Oh, hi guys, welcome back to the channel. This is structural analysis made fun and easy, but we're looking at retaining wall today, starting on retaining walls. So there's still structural engineering. I was doing a retaining wall. I need to brush up on the basics. So we got the old copy of Soil Mechanics by R.F. Craig from my University of Southampton days. All copyright to Chapman and Hall, R.F. Craig. So this is chapter 6, lateral earth pressures, Rankin's theory of earth pressure, lateral earth pressure. So I'm looking at example 6.1. So I've redrawn it out. Basically, he did it in like maybe one side of A5, but I just found it quite difficult. I just wanted to go through it myself to try and work out, so how he did it. So so it's example 6.1a. Calculate the total active thrust on a vertical wall 5 meter high retaining a sand of unit weight 17 kilonewtons per meter cube, for which is that delta angle of shear resistance effective is 35 degrees. The surface of the sand is horizontal when the water table is below the bottom of the wall. Part B, determine the thrust on the wall if the water table rises to level 2 meters below the surface of the sand. The saturated unit weight of the sand is 20 kilonewtons per meter cubed. So there's a little diagram, figure 6.6. Here it is. Figure 6.6, and you've got a retaining wall, just a vertical wall, 5 meters high, and then you've got 2 meters. In part A, there's just 5 meters of plain wall, which, if we look at my diagram, so I'll show you in a second. Figure 6.6 is for part B. Ka, Ka from the preceding chapter is equal to 1 minus sine 35 divided by 1 plus sine 35 equals 0.27. So the question was, calculate the total active thrust. Calculate the total active thrust on a vertical wall 5 meter high retaining sand of unit weight 17 kilonewton per meter cube, for which phi equals 35. The surface of the sand is horizontal and the water table is below the bottom of the wall. So that's part A. So that where it says PA, I think isn't that supposed to be FA, force active? And that's just basically like hydrostatic pressure. So that is equal to the area. This is the area of the triangle. So first within there, you've got to find PA at the pressure active at the bottom of the wall, which is equal to Ka times gamma, the unit weight of the material times H, like hydrostatics. So that is 0.27 times 17 times 5, and then to get the force A, that's then the area of the triangle of that triangle is half times PA times H. So it's half times 0.27 times 17 times 5 squared. That's equal to 57.5 kilonewtons per meter. So I just went over that on my. Sorry, but it's a bit messy. But this is where I rewrote the question. Okay, so this is for part A. Use Rankin's theory of soil pressure. Active soil pressure coefficient is Ka. 1 minus sine 35 divided by 1 plus sine 35 equals 0.27. The calculation as presented in the book. So I put that as FA instead of PA, as I just explained, 57. So then I'm just drawing it out here. So you basically had the 5 meter high wall with the ground level behind it. So the pressure diagram from the soil is just a triangle. It's just a simple triangle, right angle triangle, and then the force of the soil. It should be at 2/3, shouldn't it? 2/3 of depth. K01. Yeah, the water table is below the level of the base of the wall. The water table is below the base of the wall. So I call that F. So PA is the pressure at the base of the wall. PA is equal to Ka times gamma weight of the soil times depth. Yeah, that's what I said. So it's 0.27 times 17 times 5, and then FA is the area of that triangle, which is half PA times A times H, and PA is KAYH. So FA is half KAYH squared. So step 01 is to work out the active soil pressure coefficient, which is based on the angle of internal friction, i.e. the strength. Oh yeah, the strength. Yeah, so that Ka is 1 minus sine 35 plus divided by 1 plus sine 35. W, what gamma weight is the base unit weight of the soil. H is the height of the soil. FA is the area of the triangle, which is half times B times H. B equals PA, and PA equals Ka gamma weight times H. This is a very simple warm-up question, and just to get started. So that's, I agreed with him that it is 57.5 kilonewtons per meter. I just double check that calculator. Calculator. It is and so the pressure at the base of the wall is 0.27 times 17 times 5, 22.95, and the force is then times 0.5 times 5, 57.375. 57.5. Okay, I got 57.375 and he's got 57.5, but that's close enough for me. Okay, so then part B is determine the thrust on the wall if the water table rises to a level 2 meters below the surface of the sand. The saturated unit weight of the sand is 20 kilonewtons per meter cubed. So that is part B. The pressure distribution on the wall is now shown in figure 6.3, including hydrostatic pressure on the lower 3 meters of the wall. The components of the thrust are, so he's done the triangles. He's got one triangle here, the top 2 meters high, and then I think that 2 is like the surcharge from 1, like a surcharge from 1 on the wet sand. So that's area 2, and then 3 is the active weight of the sand behind the wall at 3, and 4 is the hydrostatic pressure. So we've got section 1, as per part A, is the normal soil weight is 0.27 times 17 times 2, and then the area of that triangle is half times base times height. So that's half times 0.27 times 17 times 2 squared is 9.2 kilonewtons per meter. So I agree with that. Then section 2 is Ka times the surcharge from the sand above the water table. The sand above the water table is 17 times 2, and the force altogether is, so the pressure is 0.27 times 17 times 2, and the whole area of that, the force of that triangle, the force of that rectangle, 0.27 times 17 times 2 times 3 is times the height, 27.6, and then 3 is 0.5 times 0.27 times 20 minus, so basically for section 3, so the saturated unit weight of the sand is 20. So we're going to calculate the hydrostatic pressure in 4. So take away the hydrostatic pressure, which is 9.8. So 20 minus 9.8 is equal to 11.2. So for 3, triangle number 3, the pressure at the base is Ka times gamma weight times unit weight times 3 height, which is 0.27 times 11.2 times 3, and then the area of that triangle is half half times 0.27 times 11.2 times 3. So that whole equation is half times 0.27 times 11.2 times 3 squared equals 12.4. And section 4 is just a simple hydrostatic, just the hydrostatic part of it, which is half times 9.8 times 3 squared, because that's the pressure of that is 9.8 times 3, and the area is the area of the triangle, which is half times height times base, so that's 9.8 times 3 times 3 times half, which is 44.1. So the total thrust is the sum of those: 9.2, 27.6, 12.4, 44.1. So that's, say, 2 plus 6 is 8, plus 4 is 12, plus 1 is 13, so that's 3 plus 1. Then 9 plus 7 is 16, plus 2, that's 18, 20, plus... 9 plus 7 is 16, plus 2 is 18, plus 4, that's 22, plus the 1 carried forward, that's 3. Wasn't it carry 2? 2 and 1 is 3, plus 7. Oh yeah, 20, that's 93.3. So I got the same as that in the end. I just went through, I just gone through in a bit more detail here. So triangle number 1, this is triangle number 1. Triangle number 1, this is 2 meter high. So on his diagram, triangle number 1 here, this is 2 meter high because it is 2 meters below the surface. In more detail, gamma, the dry weight of the sand is 17 kilonewtons per meters cubed. So this is dry soil. The PA, pressure at the base, PA equals Ka times unit weight of soil times H, which is equal to K as per above, the same soil. Ka is 0.27, so PA is 0.27 times 17 times 2 equals 9.18 kilonewton per meter squared, and FA is the area of the triangle, equals half times base times height equals half times 9.81 times, so it's half times 9.81 times 2, which is height, equals 9.81, so I agree with the text. Section, the triangle, he's got section 2. The saturated unit weight of the sand is 20 kilonewtons per meter cube. The section is, sorry about the scribbles on there. Section 2 is in detail, 3 meters high. 3 meters high, and it is the PA is equal to, this is the surcharge section of the soil above the dry soil. PA is equal to the pressure at the base of the base of the wall, 5 meters, and FA is acting at half the rectangle. So PA equals Ka times unit weight of the soil times, there's a surcharge above, times the H above, constant, not triangular. So it's 0.27 times 17 times 2, which is 9.81. Oh yeah, so the FA, because it's rectangular, so FA, that's the area of the triangle, equals 9.81 times the height, because it's just base times height. 9.81 times 3 is 27.6, so that's what he got. Yeah, 27.6, I got the same. So it's basically, the surcharge of the soil above is 17 times 2, which is 34, and then times that by Ka. That's the bit I didn't get. It's just 17 times 2 times Ka. My back's starting to hurt. So then section 3. Oh my goodness. So the unit load of the soil weight is 20, and the unit weight of water is 9.8. So the if you take away the water from that, it's 11.2, and 0.27 times. Section 3. So we want the PA at the base of the triangle for the dry component of the wet sand. So that is that's Ka times unit weight times 3, which is 10.2 times 3 times 0.27, and then the FA is PA times H, which is 3 times half, because it's half. So PA equals Ka times 10.2 times 3. Times times half times 3. So that PA is wrong. This PA in bolder blue is wrong. Where I've written that over here is wrong. I mean, PA is 0.27 times 10.2 times 3 is 8.262, and FA is the area of the triangle, which is half times PA times H, which is 8.262 times half times 3 is 12.4 kilonewtons. That's what he's got on his one, isn't it? 12.2. And so the final section of the triangle is 4. So it's 0.5 times 9.8 times 3 squared, because the pressure at the base of the triangle is 3 times 9.8. So, and the forces half times the pressure times the height. So it's 3 times 0.5 times 9.8 times 3, which gives you 9.8. Gives you 44.1. So you just add them all up. I just summarize some of the parts to make a total. So section triangle 1, 9.2 kilonewtons per meter run. So that's a dry sand above the water table. Then 2, 27.6 kilonewtons per run, which is a dry soil surcharge on the wet sand. Dry sand surcharge on the wet sand. Section 3, which is rectangular. Then section 3 is 12.4, which is the dry component of the wet sand. That's section 3, and then section 4 is the water hydrostatic. So that's quite big, 44.1, and the whole force is 99.3 kilonewtons per meter run. I hope you enjoyed this video. Got to cut it short because just late for lunch and stuff. Hopefully you found this video useful, and if you liked it, please can you like and subscribe, and then I try and redraw the presentation a bit better, so it's got some scribbles on it. But just wanted to show you, like, I think, like, on these things sometimes they could break it down a bit more for us. Even a simple example, just when you're starting out, you need it kind of broken down, because the book's quite, like I was saying on the other video, the book is in A5. The book is in A5 format, and the text is quite, I don't know how big the text is, quite small. I'll measure it in a minute, but I find it hard to read, and it's not even an example on one sheet. It's just, I find it hard to follow them. So hopefully you found this video useful, and then please like and subscribe to the channel, and then I can do some more videos. Thanks for watching. I'll see you in the next video. Bye.